Hello, Yasmina. Thank you very much. Yeah, as we were saying, the subject today is enterprise data workflows. And I'd like to start out by going through some of the definitions of what we're talking about here. The big data space is appropriately very big in terms of definitions. And one of the things that in particular I want to point out is a little bit about the origins of where some of what we're talking about came from. So rolling the clock back to about 2001, there was sort of a start of recognition of maybe a little bit different approach. Amazon was definitely becoming a success story. Google, you could start to see some of this coming about, Yahoo, et cetera. eBay was another one of the big ones. So there is an excellent paper from that time period. It's by a former stats professor at Berkeley, Leo Brennan, and it's called Statistical Modeling: The Two Cultures. And I'm just fascinated by this paper because it really chronicled a kind of sea change that was happening in the industry at the time, shifting away from a previous mode of what, when I went to school, we would have called it data modeling, into a newer mode of what Brennan calls algorithmic modeling, essentially machine learning, and also shifting away from the idea of an analyst working on a workstation or a spreadsheet, something like that, into more of the notion of interdisciplinary teams working on relatively large-scale problems, probably using some kind of cluster computing. So I highly recommend this paper. It made a lot of waves, and definitely some professors from around the world sent in rebuttals. Bremen went and published those, as well as some rather humorous remarks, very insightful remarks. So I definitely recommend this as kind of a starting point for where do we start to see some analysis of machine learning, big data, data science. And going from there, over the past several years, I've been leading teams that work with very large-scale data applications, building recommender systems, anti-fraud, different types of social network analysis, et cetera. And on these teams, I think it's very important to talk a bit about the kind of process. How do we think about the problem of approaching very large-scale data and surfacing insights? One of the tools I use, and I try to compare notes with my peers as much as possible, and definitely we see a similar kind of view used by many others. I have a 5-step process in terms of starting out with discovery, going into the data, trying to understand what's there, what's not there, really helping to get to the right questions to ask about the data. And then from there, going into more sophisticated work in terms of modeling, the machine learning, the predictive analytics, et cetera. Usually that's leading towards some kind of automation. And that's a really different skill set than, say, running ad hoc queries and doing reports. You're getting into algorithms, you're getting into a lot of stats. And then from there, it's interesting because you really start to pull in more of the multidisciplinary aspects. You're involving large-scale systems, distributed systems, so you're involving ops, DevOps kind of people for infrastructure. You're involving the applications developers who are working at a layer above, but are maybe not so much working in the statistics and machine learning. And what I've found in my experience is that actually leadership really depends on kind of a middle part, the integration. How do you pull these different disparate disciplines together into one cohesive team, producing apps, producing insights? Now, I preface that kind of leading up to what's the notion of a workflow. Along with the notion of process, we have people on teams, interdisciplinary teams. And I work with a model where there's really 4 different roles that we talk about. There's the domain expert, there's the scientist or analyst, there's the application developer, and then there's the ops people. And I really do try to use a lot of pairing to get people with very different skill sets working together side by side on the same problem. Might have a statistician working next to a Linux systems engineer, because sometimes that's the only way to really knock down the problem. Now, if you take those 5 processes, steps, by those 4 roles, do a cross-product there. You end up with a matrix. I use this as kind of a management tool when we're looking at big data problems. How do we assess the requirements that we have versus the team and the resources that we have available? Where are the relative strengths and weaknesses? And we can go into this in more detail, but it's kind of a nice visual of understanding where does team and process and requirements all fit together. Now, one thing that I want to really point out about this is that discovery, the first step of just getting into the data and figuring out what's there, doing some queries, doing some reports, etc., visualization, that part of it, it really is a lot of what people do. It tends to be a relatively simple part of the problem. And going back to Bremen's argument from 2001 about two cultures, this first tip of discovery, this is kind of what the older era was really focusing on. This is more a matter of, hey, can we go into a database and do some queries? And for a lot of organizations, that's as far as they're going to go. But when we're really talking about big data and the high return on investment for certain types of apps, there's much more sophisticated work. So I want to underscore that the rest of the problem tends to be much more complex. If you've got a use case that just requires you to do some queries and some reports, that's great. But most of the time we see workflows being much more complex. And this is where I'd like to draw a dividing line between what we might call a relatively simple data flow and a more complex kind of workflow. The notion of data flow is you can probably represent it as some kind of query, some kind of script that you run. It's probably running within a single tool. And again, this kind of harkens back to notions of, say, business intelligence as far as a level of sophistication. When you're getting into more complex applications involving large-scale data, the notion of workflow, the connotation there is that you're involving people along with machines. You have a much more complex process. So, for instance, if you're working with, say, a petabyte of customer data, tens or hundreds of millions of customers that you're looking through, some of that may be wrong. For whatever reason, some of the customer records may be wrong. And when you're streaming through that data, maybe you find that some of the records are wrong. You have to pull those aside and send it off to customer support. So even though part of the workflow might be automated, other parts involve manual review and involve decisions and input by people. So when I'm talking about workflows, I really want to underscore this. That it's something that typically crosses different organizations or different departments within an organization. It typically crosses different disciplines. It may be part support, part operations, part finance, etc. There's probably more than one app involved. And when you talk about tooling, the notion of one size fits all is anathema. It's just really a fatal flaw when people start thinking about having one tool to do everything. Also, properties such as schema and provenance become really important when you're in workflow because responsibilities are crossing different teams, different departments, etc. So that's data flow versus workflow. Now, one other point about culture, there's a great article by Steve Yegi at Google. I have the link there for it. And it was actually intended to be kind of controversial, intended to be a discussion point. But Steve Yegi draws out a kind of spectrum of what he calls conservatism all the way over to liberalism. And it doesn't have to do with politics. It has to do with software engineering. What kind of environment do you have for software engineering? I'll pick on Pinterest because I like Pinterest a lot. I think it's kind of a classic over on the liberalism side of the spectrum. Pinterest, if they push out a change and maybe there's some kind of bug, no problem. They can push out another change real quick and fix it. It's all in the name of innovation. It's very fast iteration. It's very, very much in cooperation with their customer base. Whereas when you talk about, say, your bank or your airline, your hospital, you don't want them doing that. So there's real reasons within our economy, within our culture for having this kind of spectrum and very different approaches to how we handle computer software and automation. And this really comes out. It's borne out as well in the big data space. Definitely you see tools for more data flow, which are very popular with more of the early adopters, more on the liberalism side. Hive and Pig being notable because they're part of Apache, and they're really convenient to get in and get some quick answers. But when you need to put together a workflow that has some risk behind it, such as you would in healthcare or transportation or finance, this is where you get a very different kind of tooling. And today we're going to focus a lot on cascading. Again, those three verticals, finance, transportation, healthcare, had a lot of resonance early on with cascading, even though there's a diversity of verticals now. But I want you to keep that in mind, that different tools tend to go with different kinds of risk and different types of culture, and there's great reasons for that. Okay, so having said that, let me cut into kind of a design pattern that we're seeing in industry. Over the past couple of years, I've had the privilege of going out and talking with a lot of different startups, a lot of different enterprise IT shops, really trying to understand where their use cases, try to generalize from that and elevate some of the best practices and learnings from them. And there's a kind of emerging design pattern for data workflows that we see in big data. You could think of this almost as a kind of middleware that's emerging. And there's three vendors that I'd like to spotlight in particular, which are working in different kinds of trade-offs in this area. Concurrent, doing cascading, definitely, and also with Lingual and Pattern as other components of this. Actian also has ParAccel, and they've done some really excellent integration with Knime and Eclipse and others. Arguably also very, very interesting workflow. Also on the Python side of the world, we definitely see a lot of groundswell, a lot of growth of Python being adopted in this area. I think that Continuum Analytics with the Anaconda platform, what they're doing, as well as having IPython on top of that, Pandas, Augustus from Open Data, et cetera. There's a lot of really interesting work in the Python side as well. I'm going to focus on concurrent and cascading. That's what the subject of the book was about. Okay, so as far as a design pattern, we see this over and over, and in fact, I'm struggling to find use cases for something different for other design patterns. But typically, you start out with multiple data sources, data coming from different types of frameworks. Maybe it's some customer profiles and then some log files based on those customers, but typically some heterogeneous sources. From there, you go into some kind of ETL process, which is extract, transform, load. You're loading data into your cluster, for instance. And from there, some kind of data preparation. Typically we talk about this being 80% of the problem, really cleaning up the data, especially when you come into big data, unstructured big data. From there, typically some kind of predictive modeling, something to juice up the data, refine the results. This is where the machine learning parts come in. And from there, getting pushed out into line of business use cases, the end uses. Now, looking across an enterprise, the ETL, frankly, SQL gets used for this a lot. Frankly, Teradata is one of the really big vendors in that space. And it's interesting because, as Julian Hyde from Optique points out, looking at ANSI SQL uses across enterprise over a number of years, really the long tail, the bulk of the SQL usage is for ETL. And it's for data which will never be normalized, never be indexed. You're just using SQL as a way of capturing the business logic. Now, over in terms of data preparation, people write Java code and Pig and whatnot in enterprise to do this kind of data preparation, cleaning up the data. Typically, that's done by some department before the analysts and the scientists get their hands on the data. I think that, I'll reference DJ Patil and other notable data scientists who've said over and over that the data preparation is like 80% of your work, always. And, as soon as you get some kind of product out there, the stakeholders come back and say, hey, add the following 3 features, you're back to square one. With unstructured data, you have to go back and do more data preparation. And as you bring in new sources, of course, that happens too. DJ Patil makes the point in a couple of O'Reilly books that really the data preparation is data science. That's the bulk of it. That's really what you're contributing a lot. Now, in terms of predictive modeling, when we look across enterprise, of course, SAS, that company has a real huge market share for modeling, especially in finance and other kinds of verticals like that, healthcare, et cetera. We also see a lot of usage of R or maybe MicroStrategy, Teradata, et cetera. What's interesting when you look at this kind of design pattern is that in large-scale data workflows, most of the licensing cost that we see in is very in the predictive modeling. Respectively, Teradata and SAS, of course, take a lot of that off the table. And yet most of the project cost, the time that the people on your team spend, is typically, like I say, 80% in data preparation. So those three rectangles at the top of this kind of design pattern, they're what take up most of the cost. So introducing the notion of what's been going on in Cascading, there are open source components for each one of these boxes in this design pattern. There are certainly source taps that provide formal integration for a number of different data frameworks, Cassandra, HBase, et cetera. And that way, by having formal integration, not only do you get the compiled app, but you also you inherit schema and some notions of data lineage, data provenance. In terms of ETL, there's a project called Lingual, which is an ANSI SQL on top of Cascading, compiles down to Hadoop jobs in Cascading. And then, of course, the business logic part, the data preparation, that's what people were using Cascading for, for the past, going on 6 years. More recently, for the predictive modeling, there's a project called Pattern. It's very much early on, where, like 6 companies now have contributed, basically taking PMML so that you can export predictive models out of SAS or other frameworks. You can export them as XML. It's a standard called PMML. And then Cascading can read that in and generate the Hadoop jobs. And then, of course, there's formal integrations as well for the end uses, the results. Usually those will not be consumed directly out of Hadoop. Those will tend to be consumed out of, say, HBase or Metacache, maybe MongoDB, things like this. Now, what's interesting is that by using a workflow framework like Cascading, you're able to take this entire design pattern, all these 5 steps, which in enterprise may be crossing 5 or more departments, and you're able to put it into one integrated workflow. The compiler sees this as one connected graph. We call it a directed acyclic graph. So the compiler sees this, all the business logic of this in one graph, even though parts of it may have come in as SQL or parts of it may have come from SPSS. And so that's interesting because now the compiler has the opportunity to do optimization. It also helps your team to be able to do troubleshooting in a more consistent way, coherent way. Much better opportunities for exception handling, notifications, understanding utilization rates, etc. To try to show here a bit of code of what I'm talking about, if you were to take SQL, whether it's coming out of DB2 or Teradata or Oracle or wherever, you can essentially cut and paste the SQL queries. So based on the uptake library combined with Cascading into what's now called Lingual, is the open source project, it's really only a few lines of code. We define a flow def. We describe where the sources of the data are. In SQL terms, think of this as the from statements, the tables. And then we describe where the results that would go in terms of the sync. Then we call a SQL planner. And in purple, there's a variable SQL statement. Think of that as a command line argument that you're providing to your Cascading app. And that would literally be the query that's coming out of Teradata or DB2. And then from there, you call an assembly planner. And essentially, it creates a subassembly. It generates all the Cascading calls and sort of welds that part of the pipeline into the rest of your app. Similarly, for the predictive modeling side, whether you're working with R or SAS or SPSS, things like this, It's a fairly similar kind of code there. Again, just a few lines. We have a flow def. We define where the input data is going to come from and where the output data will be routed to, where the sync will be. From there, we call a PMML planner. Similarly, the purple variable PMML model, you can think of that as like a command line argument, and it's specifying a model that you've exported out of SAS or R. It might be, say, a random forest or logistic regression, or some kind of model. From there, we called an assembly planner, and it generates all the cascading calls and effectively welds that into the pipeline. So at a higher level, let's pull back a bit and look at this, what an app would typically look like. Again, this might be something that's deployed in enterprise that typically requires work product from several different departments. But at the end of the day, it's one connected graph. It's a workflow. It defines the business logic of how this app will interact with the different departments. The data being loaded, the result being consumed. If there's exceptional data, where will those traps be routed out to, I don't know, customer support or audit or wherever. And in the notion of cascading, as well as some of these other workflow environments, there's visual metaphors for being able to comprehend the business logic and how it all ties together. That really helps in the collaboration. Okay, so let me shift gears a bit. We'll drill down into cascading and some more of the content from the book here. So the author of Cascading, Chris Wenzel, he was a system architect at Thomson, which is now Thomson Reuters. And rolling the clock back to circa 2005, he was evaluating a project called Nudge, open source project for essentially web crawling, web search, web indexing. And out of Nudge, of course, came Lucene and Hadoop. 2005, this was back before Hadoop really even had a name, but they were starting to consider it. And so Chris Wenzel was evaluating this open source project, trying to understand, could this new open source technology for handling big data, could this be taken into an enterprise context and be leveraged by, say, Thomson? And, one of the takeaways was it was going to be stressing the limits of how many expert Java developers could you get who really understood the details of Hadoop. And that's a problem even today. We really, in the industry, cannot hire enough Hadoop experts. There aren't enough to go around for the needs of enterprise. So one of the takeaways that Chris had was, there's a real need for a kind of abstraction layer on top of Hadoop so that people who are expert with Java in more of a J2E kind of environment, for instance, so they can jump right in and just start using an API. And that's where cascading came from. A key insight, though, was that when you look at the early papers on macros, go back to Google's original paper, 15 and all, they make a very strong point of how much they've leveraged functional programming. And this goes back to what the AI community was doing at MIT, Stanford, CMU, et cetera, back in the 70s and 80s. And I got in the game as an AI grad student at Stanford back in the early to mid-80s. So I can definitely resonate with that pretty well. Functional programming really comes in handy with big data. And also, when you look at the typical use cases for Apache Hadoop, it's usually data workflows, data pipelines, and that fits really well with functional programming. So the introduction of cascading in late 2007 was to introduce a notion of functional programming for data pipelines, for these workflows within Java. And that serves 2 points. One is people who already have the Java expertise, the JVM language expertise, they can go right in and leverage it without having to become experts in Hadoop. And then number 2, enterprise, which probably has already made a lot of investments in tooling for JVM on their clusters, they can leverage that as well for Hadoop. It's very interesting to me also, if you go back to some of the original work, Edgar Codd, et cetera, about relational model, is kind of leaning towards this view of how to handle large-scale data workflows. He was talking about specific languages that were embedded in terms of other programming languages. And it fits really well with the cascading model, as it has been borne out by some other open source projects on top of it. In particular, two of those projects, one is called Cascalog and the other is Scalding. And really for most of the use cases that we see, the new deployments with cascading, they tend to be using one or the other of these. Cascalog is in Clojure, Scalding is in Scala. Both of them have been supported very much at Twitter. For instance, about half of Twitter's compute actually is based on this, primarily Scalding. Although the really largest use cases that we see for cascading, talking about factual and climate and some other really large-scale cluster computing, those mostly use Cascalog, Nokia, Telefonica, etc. The point I wanted to make, though, about functional programming is that proof is in the pudding. Over the past 5-6 years, companies like Twitter, eBay, LinkedIn, Nokia, and others have invested a lot to build out open source projects based on Clojure and Scala, and then in turn, they have built their revenue apps in these open source projects. Cascading is foundational. It's underneath these projects. It's almost like assembly language programming for functional programming and big data. And there's a great article by Dan Woods from earlier this year where in Forbes, he really calls out some of these aspects. Okay, now I have a little bit of a comparison here. I work with my friends who are very much Hive experts who try to do a good apples-to-apples comparison of the same program written in Hive, Apache Hive, versus Scalding. And we see about a 3-to-1 difference in the amount of source code. And up across the board, we see that as well. We'll drill down in this a bit more. I did want to make the point that cascading has a lot of deployments. There's sort of the obligatory slide here of different company icons, but a lot of large deployments across a lot of verticals. Let me shift gears for a moment and talk a little bit about theory, and we'll come back to code here in a moment. One of the important points about workflow abstraction for big data, one of the important points about cascading is that, formally speaking, we call it a pattern language. Pattern language came out of architecture, where you wanted to have a way of conveying expertise, a way of representing best practices, so that people who weren't necessarily experts in a domain could still have their contributions be integrated. In another way of thinking of this, when kiddos are playing with, say, Lego blocks, building a tower out of Legos, if you snap the Lego blocks together correctly, you have some properties guaranteed of their stability for the tower to be able to stand up. If you don't snap the blocks together correctly, the tower will probably fall over. So that's the idea of a pattern language, that if you take the components and snap them together in the ways that are allowed, that are intended, then you have some guarantees of how the entire structure will work. In the case of cascading, it uses a plumbing metaphor, like building data pipelines. And so you construct a graph to represent the business logic of your application using these pattern language components. And as they snap together correctly, then you have some guarantees of how the compiler would be able to make this app run at scale, run in parallel at scale. Another theoretical point that's really interesting is it comes from Don Knuth. He had a book called Literate Programming, where he talks about putting the emphasis more on when you're writing code, the intention is to be telling other people what you want the computers to do. The intention is not to be telling the computer what to do. That's a subtle point, but the idea here is borne out in cascading, where you're working with this pattern language and you're representing the business logic. You're telling other people across your organization what this app is going to do. And you let the computers, the compiler, the flow planner, et cetera, figure out underneath what it's going to do. So that leads to a kind of separation of concerns. At a high level, you work with the business logic. At the low level, the flow planner and the compiler are handling the parallelization. By virtue of having the pattern language, it gives you kind of a 1-2 punch, giving those guarantees to the compiler. So in a nutshell, that's really kind of the theory behind what's going on with cascading. If you want to dive into more theoretical aspects, I highly recommend a paper by Mosley and Marks. It's called Out of the Tar Pit. It's one of my favorite papers in software engineering. They talk about functional relational programming, and they really do reference cascading. Cascalog in particular has been cited as one of the rare instances of what Moseley and Marks are trying to bring out. Okay, so we'll shift into some code samples here. First off, word count. We use word count a lot when we're talking about parallel programming, MapReduce in particular. And the idea is that word count is a very simple, concise, very short amount of code to represent it. But yet it requires some symbolic processing. It requires some numeric processing. Parts of it can be parallelized. Parts of it cannot be parallelized. So if you can run word count efficiently in parallel at scale on a given framework, then you have some guarantees that a much broader class of more interesting, more valuable kinds of complex problems can also be done efficiently in parallel at scale. So we use word count kind of like a canary in a coal mine. Now here, in terms of pattern language and cascading, a word count is represented as a graph. We start out with a collection of text documents. These flow through the pipeline. We apply a function to tokenize the text. So downstream from that, we've got essentially a stream of keywords, tokens. We apply another function, aggregation, to do a group by. This is very much like a group by in SQL. And so downstream from that, all the tokens are arranged into their groups. And then we apply another function to count each group. And then we emit the end results, which are effectively count and token for each group. That's a word count. This is definitely shown in the book, but there's also a series of blog posts that go through step by step a lot of the code that we're examining in the book. Step by step, how to build cascading apps, starting out from the simplest possible cascading app into a fairly detailed implementation. Okay, let me get back in. I know there's been a couple of questions coming up. I want to get through another section here, and then we'll start to address some of these questions here. And I'd like to do some more of the Q&A towards the end, though. But please have the questions coming through. It's much appreciated. In terms of the source code for cascading, the graph that I was showing there for word count works out to being about 18 lines in Java. And that's notable when you consider that the word count which ships with Apache Hadoop is 3 times that size. So already by virtue of using this functional programming kind of metaphor for pipelines, we get a reduction in code volume. It's also interesting, too, that almost all of the 18 lines of code up until the last one, the first 17 lines, do not happen on the cluster. Those happen on the client side before the jobs are submitted to the cluster. And so really most of the code is executing to build up the graph, which will then be serialized and run in parallel on the cluster. That's important because you want a framework like Cascading to run through your business logic, again, run through the pattern language rules as much as possible up front to determine if there are problems in advance before you start burning time on your cluster. Speaking as an engineering director, you never want your team troubleshooting on the production cluster. It's just a great way to waste money and time. So the first part of this is all run on the cluster side, on the client side, and then the last line is actually where the jobs get submitted to the cluster. The second to the last line actually takes that graph, that business logic, and writes it out. So as you maybe we'll see here. If not, we've got this online in a lot of places. It's actually a dot file. If you have GraphViz or OmniGraph or Visio, you can open this up. But it is the business logic that will be executed on a cluster. What's interesting about the cascading community is when I first started looking at it, I saw people who were novices popping up and saying, hey, I'm trying this out. I got stuck on a certain point. And some expert will pop up in a different part of the world and say, show me your flow diagram. And even before asking to see source code, they would ask to see the flow diagrams. So that really gets back to Don Knuth's point about literate programming. This is the business logic. It's very graphical in nature. And even though some of the elements here may have come out of SQL or SPSS or something, it's still represented as a common graph. Let me shift gears a bit. In Cascalog, you're working in a language called Clojure, Cascading in Clojure. And really the first part of this is what we call a namespace. It's basically, if you're familiar with Java, it's the imports build instructions. And then there's a 3-line function that's defined. We could have done that inline. Paul Lamb wrote this version of it. I was working with Paul on some other parts of this. For pedagogical reasons, we included a function. We could have done that one line inline as well. So the actual word count in Cascalog turns out to be 6 lines of code. That's an order of magnitude reduction in code volume compared with if you just wrote it in Hadoop in Java. And really, we see this across the board. When you take a look at Cascalog applications side by side with the same business logic implemented in SQL or Java, you see an order of magnitude reduction in code volume. And there are very serious consequences of that for engineering teams. This is why for the very largest MapReduce applications we see in Cascading, almost all of those are represented in Cascalog. Again, Climate Core, Factual, Telefonica, Nokia, etc. And the reason is that you can have a relatively small engineering team grappling with a very complex problem, but with a small code base to maintain. Obvious benefits for that. Cascalog is an implementation of something called datalog. If you've ever heard of a programming language called Prolog, datalog is a variant of it. And so really here you're working with Prolog implemented in Lisp, implemented in Java. and that's a little complex for some people. For those who really like Prolog and Lisp, of course, it's familiar territory. One thing that's very interesting about Cascalog is that you can work from a prompt, what's called a REPL, and you can issue ad hoc queries from the prompt and get answers back. With Cascalog, going from an ad hoc query to a function is about 1 line of code. And then because the functions themselves are really statements of logical predicates about the data, going from a function to a unit test is usually about 1 line of code using the midge package. And you build your apps up by composing these functions. So it's really interesting with Cascalog that you can go from ad hoc queries all the way up to having a full application with unit test coverage at scale in just in relatively few lines of code. Going back to my process model for data science, the 5 steps of discovery and modeling, etc. This is great because Cascalog provides a full software development lifecycle, and that's relatively unique in the world of big data. On the one hand, we see these really large deployments. On the other hand, there is a learning curve. Clojure is not something a lot of people really resonate with. You won't find as many developers there, but those of us who do use it really love it. Aggregators are usually the magical part. It takes a while to just focus on those and do those over and over until you learn them. In contrast, Scalding is cascading in Scala, a Scala language. And when you look at this, it's functional programming, but it's much more straightforward. From a computer science perspective, there's an almost one-to-one correspondence between the function calls in Scalding and the elements in the flow diagram. And that really gets back again to what Knut was saying about literate programming. From a computer scientist perspective, we would call that elision, very efficient language elision. In other words, there's no fluff. So from an engineering perspective, that's great. That means that a team can go out and write Scalding apps, and another team can pick up the same code 9 months later and be able to understand what they were doing. So I find that Scalding has a lot of affinity in enterprise, especially in organizations where different departments communicate via data APIs and need to have the hygiene on those APIs. Scala has great properties for that. As well, Twitter and Etsy and eBay and others have invested a lot to have some libraries. 2 in particular that I'll call out. One is the Matrix API for linear algebra, working with sparse matrices, and the other is Algebird for abstract algebra. So if you're familiar with some of the streaming algorithms, sketch algorithms, count and sketch, things like that, running medians, those are leveraging abstract algebra, and very interesting work in machine learning these days. So, Twitter and others have built out their revenue apps using these kind of libraries, and by leveraging Scalding, the organization can just grab that right off the shelf. Now, in contrast, Apache Hive for the same application, it's very concise, very compact. But I want to bring out the point that Hive is good for the smaller kinds of applications. Once you get into more complex applications, it becomes much, much more complex. relatively speaking, to maintain this and to understand it. Hive also has a non-deterministic flow planner, which means that it'll try a strategy. If it doesn't work, it'll backtrack and try a different strategy. So actually troubleshooting it on the production cluster becomes a very costly thing, and I can attest to that. I've run teams that use Hive at very large scale, and it's great for the right uses. But when you're talking about workflows and not data flows, the workflows incur a lot more complexity, a lot more interaction with people, and Hive is probably not the right tool there. Similarly, with Apache Pig, in terms of business logic, it looks similar to the Cascading program. It's very different in some ways. On one hand, Apache Pig is formally speaking what we call a data markup language. A DML. It's not a compiled language. Whereas with Cascading, you actually are working in Java. You are working in Scala with Scalding or Clojure with Cascalog. In Pig, you've got a separation away from the compiler. And one of the problems there is that if you want to extend it, you end up writing UDFs. And Vitaly Gordon makes the point of what he found when he joined LinkedIn. There were actually production apps that were written. There's one that he shows in his slide deck where it was a Python program that had a Pig script inside of it that called out to a Java UDF. And in the space of 20 lines of code, you'd cross through 3 different languages. And the problem is that if you're trying to troubleshoot that at scale, the engineering costs go through the roof because trying to track down exceptions across different language barriers becomes extremely expensive. So Pig is great for what it's used for. Again, for workflows in an enterprise setting, more complex workflows, probably not the best. Now, let's talk a little bit about use cases for these kinds of languages. And let me illustrate, say, in an agricultural vertical, something like a Caterpillar or John Deere. And I wanted to underscore that when Caterpillar or John Deere, when they're thinking about data science and big data, they're not building a social network or a search engine. they're optimizing multi-billion-dollar supply chains, and they're building heavy equipment. It's a $250 billion market segment. A lot of operations research, a lot of really complex workflows, and that's an example of like an enterprise incumbent. On the other hand, really arguably in the same vertical, think about a company like Climate Corporation, which is a 200-person startup, really, but they're also working with a lot of data in the way that, say, John Deere is creating drones and getting a lot of remote sensing about agricultural optimization. Climate Corp is also looking at these problems to produce insurance for farmers. So the kind of flip sides of the same coin. One is a very large enterprise incumbent. The other is a startup. And we see that, in these different verticals, we really see these two kinds of organizations being connected on the same curve. On the one hand, the incumbents, they're grappling with complexity all day, every day. They're grappling with scale. They've probably made large investments in terms of SQL and SAS and Java, et cetera. And the workflows have to integrate staff, which is highly trained for that. Whereas the startups crave complexity to try to get to scale, to become viable. And the new ventures that are moving into the enterprise space, we see them working with relatively lean staff. They tend to leverage more sophisticated engineering practices to keep the staff small. Cascalog and Scalding are used there a lot. At the end of the day, both of them, if they're successful, they meet in the middle in terms of complexity and scale and innovation. Okay, let's see. There's been a few questions here. Okay, there's a couple questions that I'm going to address real quickly. Strengths and weaknesses of Scalding versus Clojure. Scalding arguably is a lower level language than Clojure. There are much more interesting things that can be done with Clojure at a relatively high level in terms of machine learning and managing very complex workflows, whereas with Scalding, you will be writing more code. So on the one hand, Clojure is much more compact. Both of them are interesting because both Clojure and Scala have substantial libraries, and respectively, Cascalog and Scalding can pull in those libraries and integrate those libraries directly into the workflows. So, you may be bringing in different libraries out of Java or so. Now, the difference between Cascalog and Cascading, Cascalog is Java. Cascalog is Cascading in Clojure. It's based on Cascading. That was another question I had. And then, let's see, a couple other things. What are thoughts about the fit and adoption of Clojure in data analysis? I could go into that in much more detail. Let's hold that off to the end. We'll have some more things to talk about there. Done analysis to compare Cascading versus Crunch is another question. Yes, actually, there was MITRE actually did, and others have done some pretty large-scale analysis, performance analysis of Cascading versus Crunch. And at the end of the day, we see this borne out in really large-scale use cases. Like I say, half of Twitter's compute is based on Scalding. Crunch doesn't have quite as much time in the seat and doesn't have quite as much in terms of integration and as many eyeballs on it. Cascading has had going on 6 years now. And part of the problem with this is that the easy problems in data workflows are also easy to do. So if you look at something like Tangool and they just knock down the easy problems, great. The hard problems are very hard. And so part of my criticism, there's been a lot of other kinds of workflow tools that come up that don't really catch a lot of traction. Generally speaking, it's because they focused on the easy problems. They didn't try tackling the hard problems. The thing is, when you look at Cascading, you've got 5 going on 6 years of enterprise deployment, tackling the hard problems and resolving them. Okay, so I think that's all of the questions except for the one about Clojure. We'll hold that off more towards the end. I'm going to shift gears. Let's see, we've got about 10 minutes here, so I'm going to go through stuff pretty quick on this part. I want to talk about a couple of libraries, Lingual and Pattern in particular. I'm going to cut through a couple of slides here and just get to Lingual. Okay, Lingual is anti-SQL on top of Cascading. One of the things that gives you is a JDBC driver, also gives you a prompt. And I showed an example here. You've got, I took the MySQL test database with a bunch of CSV files, and I ran that through Lingual. I used, let's see, this is loading here. I used the DDL from MySQL test database and applied that, and then I brought up a SQL prompt, and it brings up, I can drill down through a relational catalog. That's kind of interesting because by using this, you have not loaded the data into a relational database, but you can surface a relational catalog on top of unstructured data. Now, I did a query. This is not really intended for ad hoc queries. It's intended for batch. But in the MySQL test database, here's a query showing the results. And also here, I've done a use of JDBC. It's got a JDBC driver. It looks like most JDBC calls that I've ever done before. But I can go and apply that. For instance, here I've got an R script where I call JDBC, and I get the results back from Lingual. This is actually firing up a cascading job. Could be out on a cluster somewhere. It brings it back as a data frame in R and runs some analysis, does some visualization. As far as R is concerned, it's a data frame like any other. So this is great because you can use Lingual to integrate cascading jobs wherever you would have a JDBC connection, whether it's R or Toad or Pentaho or other kind of tools like that. Another library is called Pattern, and several different organizations work together on this. The idea is to leverage a standard called PMML, and that's been around for 16 years. We just had our first conference actually last month after 16 years, but Equifax and Visa and others have been really supportive of this. In terms of vendor coverage, almost any major framework will support exporting a model as PMML. And as far as algorithms, there's a lot of coverage from most of what's used in predictive modeling. It can also be extended. So here I've done an R script which generates a random forest off some order data and essentially creating an anti-fraud classifier. The last line, I save it off as a PMML file. Here's what the PMML looks like. I don't recommend reading that. That's what machines are for, but our team had to do that a lot. And then integrating the PMML into a cascading app is just a few lines of code, kind of what I was showing a little bit earlier in the talk. From a graphic perspective, this is the flow diagram looks like. You're just adding a PMML file as a command line argument, and it builds out a workflow based on that. And then running it is just like any other Hadoop job. It compiles down to a jar file. So that's interesting because you can export a model from SAS or SPSS and then run it on a Hadoop cluster without writing a single line of code. You can use the pre-built app via PMML. And that's very interesting because at scale, the licensing costs for SAS and other frameworks like that become pretty expensive. So organizations are looking to Hadoop and Cascading to be able to take some of that licensing off the table. All right, I want to shift gears a little bit here and talk about what's coming up with clusters. There's another question. Let me look at this real quick. Okay, there's a question about the future of open sourcing the generation of PMML. I'm under the impression that Pattern has this in mind. Oh, thank you. Great question. As far as reading PMML, that's all open source. It's in Pattern. As far as generating PMML, that's a great question. Essentially building models at scale. And that may happen more on the Hadoop side, or there are definitely efforts toward that also in the Spark side of the world, Python as well with Eclipse. So there's a few different open source efforts toward generating PMML at scale, which I think will be a great boost in the industry. I'd love to take that question offline. If Walter Elder, if you can talk to me a bit more, we can strike up a conversation on Twitter or some other forum about this. I want to talk, there's a few minutes here. Let's see. I'll go a little bit into the evolution of workflows, what's happening in cluster computing. I'll go through this part kind of quick, but you'll have the slides. If we roll the clock back to 97, that's really when we started seeing the first instances of horizontal scale-out using commodity hardware and clusters parallelizing workflows. And Amazon, eBay, Yahoo, Google, et cetera, those were the four that were really working toward that. And I like to provide primary sources. There's some great articles and videos by the people who really made that happen. I definitely recommend looking into that. Some great insights of where did this idea of MapReduce come from? Where did this idea of horizontal scale-out on clusters come from? Now, rolling the clock up to today, a number of us, we make a good living by leveraging cluster computing, very high ROI apps based on that. One of the problems that you encounter with large-scale computing is that you end up, you can get in a situation where you've got these clusters. You've got a production cluster for Hadoop and a staging cluster. You've got another cluster for, say, Storm, and then you've got your MySQL shards or your Teradata cluster. You've got your Memcache cluster. You start to look at it, and you've got 5 or 10 or 20 different clusters running. That becomes very expensive. There is a notion of being able to consolidate this all on top of Hadoop as an OS. Hortonworks and Clojure and others are really pushing that. I don't really buy the idea of Hadoop as an operating system. It's not an operating system. Linux is an operating system. CentOS and Red Hat are operating systems. But in any case, we're really grappling with the problem of death and taxes at scale. Servers will fail, and data must be moved. So, there really is more to the world than Hadoop. There's a lot of topologies that are being used. It's not one size fits all. In any kind of complex app, you tend to use more than just Hadoop. And there's definitely a need to be able to run multi-tenancy and run different frameworks on the same cluster. There's been great work out of Berkeley Amp Lab towards this, definitely with priorities towards higher utilization, lower latency, et cetera. And really, when you look at what Google has been publishing in these areas, it's very interesting. The Omega project, there's a paper, I've got linked to your video and some other resources. But they make the point that scheduling batch jobs is the easy part. Scheduling high availability services is the very hard thing. And by using Borg and now going into Omega, they're able to get huge increases in utilization by doing multi-tenancy and mixed workloads. So there's a couple papers here about that. looking at something like Yarn, Hadoop as an OS, that would be over in the left-hand column. It's more of a monolithic scheduler, which tends to hit a performance need pretty early. Looking at something like Omega, you try to smooth out that curve. And now, there is a great article about in Wired about Google Borg, and also about an open source project I'm working with. It's called Apache Mesos. Wired and others have covered this pretty well. But the idea is to use something similar to what Google's doing with Borg, to have a cluster that surfaces a homogeneous set of resources and uses isolation instead of virtual machines to be able to carve off parts of the cluster on demand as needed in very low latency, so that you can run multiple Hadoop alongside with Spark and Storm and Memcache and MySQL, etc. Okay, so there's a couple of components. There's one called Chronos, another called Marathon, that has come out as open source. It's like having distributed cron, distributed initd. And basically, these are building blocks for clusters, building distributed frameworks on top of these kind of clusters. I think we're running up pretty close on time. I'm going to scoot through a few different apps here. Sorry. Yeah. Definitely we see, let me go back. We see use of isolation instead of virtualization leads to big performance increases. OpenVZ has done some great benchmarks on that. We also see much better utilization. Airbnb did some studies on that. And there's a great book about this, actually, from some of the people at Google, talking about the different benefits, different issues. There's a couple of case studies that are out now. One at Twitter, another at Airbnb. One is on-premise at Twitter versus Airbnb being 100% in the cloud. Really going through the different types of use cases that they can mingle all together in mixed workloads, how they can get better efficiency. And this leads into data workflows because that's what you're trying to leverage. You're trying to have batch processes updating data products that are fed into services, and they will run them all together, reduce the latency, improve the utilization. A couple of case studies here. I think we're up at the end, so all right. I'll definitely put a plug in for the book about cascading enterprise data workflows. And if there's any other questions, I'm going to stay on here. Also, please feel free to contact me on Twitter. I'm currently at a company, Mesosphere. I'm chief scientist at mesosphere.io is our URL. And I'll punch that in. And if there's any other questions I can help to answer, see if there's anything we had from the end.
Excellent webcast today, Paco. We do have a couple additional questions that have come in. Are you able to see them?
I think so, yeah. If I've got okay, great. There's a difference between, okay, great. Yeah, sorry, I was looking at one of the tabs and not the other one. So question, is Cascading planning to support flow connectors that would run on alternatives to Hadoop MapReduce? It's definitely a great question. Cascading is not necessarily married to Hadoop. Part of the rationale with Cascading 2.0 last summer was to put anything specific to Hadoop in its own flow planner in a particular set of classes, but then expose interfaces to be able to build that out on top of other topologies. So it would make sense to have Cascading on top of, say, Spark, or on top of Titan, or on top of some type of in-memory data grid. And there have been efforts toward that. I know some of these, and I know some work that's going on under NDAs. I can't really talk about it publicly, but there have been efforts toward it. I would definitely raise that up on the developer forums for Cascading, the Google groups, because there are some people involved with that. Interesting. Great question. Agree with the statement about solving easy problems. How does Cascading help in baking in data governance into the framework? Okay, excellent question. One of the things that you want to get out of a data workflow is really a notion of tracking where did the data come from, where did it go, who used it. When you've got a large cluster and you've got a lot of apps running in a cluster, you tend to get a kind of producer-consumer relationship between the different applications. So you might have one app that's doing a lot of heavy lifting on ETL. It produces some intermediate data products. Those get stored. I don't know, maybe there's some roll-ups like week-over-week metrics, or I don't know, maybe a customer 360, something like that. But those intermediate data products get stored into a kind of some sort of ODS, HBase, something like that. And then other apps will pick those up and use them. So that's a producer-consumer kind of cascade of data products. And it becomes very important, especially in an enterprise context, to track data governance and understand, for the data product that I'm using, where did all its components come from, when was that app run, who ran it, who wrote it, which point release was it. So one of the things that Cascading is doing is being able to track effectively the schema by having source tabs and formal integrations with other data frameworks. You can understand and import the schema from those other source frameworks and then propagate it all the way through the workflow so that you have that notion of schema with your end results. And with that, also being able to track the lineage of where did this data come from, where did it go to. Concurrent is the company behind Cascading. They definitely have some things they're working on along these lines. I'm not really at liberty to talk about that openly. It's more a matter of kind of early evaluator. But definitely talk with Concurrent about this in terms of data governance baked into the framework. Let's see, other questions. Cascading plans to integrate with TES. I don't really know the answer to that. I don't really know what the roadmap is vis-a-vis TES. I've seen some slides based on that. There hasn't been a lot of open discussion in the developer community yet about it, so I wouldn't really feel comfortable about talking about roadmap or anything that's confidential. But it is interesting in the sense that there's some overlap in terms of scheduling. In the Mesos side of the world, that would probably map more towards something like Chronos, which came out of Airbnb, and a lot of other companies are adopting Chronos for complex scheduling. Scalding versus Cascalog versus Cascading. So Scala versus Clojure versus Java is another question. What are the relative merits? This is a really great question. It's something that I see organizations giving a lot of thought towards, really grappling with. Again, when you're working with complex machine learning problems, and you have relatively small teams, that's an extremely good indicator for using Clojure. And that's where we see companies like Climate and Factual and others, or even big shops like Nokia. So I'll put in a plug for Cascalog there. And the largest instances, for instance, Climate is the largest user of Hadoop on Amazon AWS. And 90% of the code base is in Cascalog. So that's kind of a distinction then between Cascalog and Scalding. Scalding, I see it really resonating where you have, say, more of an enterprise environment, where you have people who've been traditionally working in Java. Going from Java to Scala is not as much of a leap. And also when you have different departments that need to effectively shield themselves from each other by using internal data APIs, Scala is great for that. And so, Scala gets a lot of usage there. There's been great work in abstract algebra in terms of streaming algorithms, as well as in sparse matrix support, really large-scale social graphs, et cetera, that have been done in Scalding. So there's some really great libraries to use there, whether you're in a big organization or not. Twitter, LinkedIn, eBay, Etsy, these are some of the really big use cases for Scalding. And I think at the end of the day, it kind of comes down to, what does your team feel most comfortable with? You probably want to settle on one or the other. You probably don't want to do a lot of mixing and matching. But if it were me, if I were running a company, it would probably be in Cascalog. That's just my own personal preference. As far as using Java, using Cascading in Java, some of the benefits there that it is simpler to punch down and write custom classes in Cascading if you want to in Java. But certainly you can do that as well for Scalding and Cascalog. Again, I think that kind of comes back to the team. Do they feel more comfortable just working in Java? Great questions. Let me see if there's anything else that's popped up in the meantime. No, I think that is that. Yasmina, does that cover all the questions?
That looks like all the questions that have come in. I'll just peek as well one more time. I don't see anything additional. So with that, Paco, we're going to say a very, very big thank you to you for presenting today's webcast and for sharing all your knowledge and expertise.
Certainly. Thank you very much for the opportunity. I really appreciate it.
Folks that attended our event today, and we did have people from all over the world and in many places. I know it was already late, so we really appreciate you joining our event today, and we hope you found the information beneficial. And as well, we'd like to let you know, we did push out some codes to you all to save you some money as a thank you for attending the event. Paco's book, you can see it right there on the screen, it is available today for you all at a great discount for attending the event. So we hope you like what you heard and saw today and encourage you to take advantage of that discount and get the book. There is a lot more in there that can really help you with your day-to-day. Thank you again, Paco. Thank you, everyone. This will conclude today's webcast. Goodbye, everybody.